This is lecture 9A for Calculus 2. It is the introduction to the chapter on differential equations. To understand differential equations, let's start with a contrast between differential equations and the algebraic, transcendental, and radical equations that we studied in algebra. So these algebraic, transcendental, or radical equations, the function y of x is specified. In this case, it's specified as a polynomial. Here, the function, which we call f of t, is specified as an exponential. So you know the functional form of the function, and the goal is to find its value for specific values of x or t. For example, let me get the pen. Say we know that y of x is 12x squared plus 6. In other words, we know that y, this function of x, is a polynomial. Then we want to evaluate it, say, at x equals 0. So y of 0, you put that into your equation, and you get 6. That is a specific value of the polynomial. Here are two other examples. This one from chemistry. Here's the ideal gas law. So P, which is the pressure, let me find the pen here. So P, it's really a function of several variables. But let's say everything is held constant but temperature. So P is a function of temperature, and you know its form. It just has some multipliers times temperature. Okay, it's a polynomial, a first order polynomial. So you know its functional form. The goal is to evaluate the equation for certain values of n, t, or v, and thereby find the pressure. For business, the costs might be specified. So here's your cost specified as a function of x, which is the number of items manufactured. You have here 1,500, which is your, of course, your fixed cost, and 1.75, that is a variable cost. Again, the form of C is known. It is a polynomial. And the typical goal is to find the cost for specific values of x, or to plot the cost function. So in these algebraic, transcendental, or radical equations, the letters are the names of the variables. The answer is the value of the function, that is a number, or a graph of the numbers that correspond to the function at specific values. So the whole idea here is that the functional form is known. This might seem obvious, but I'm going to write it down here anyway. So here the functional form is known. And the functional form could be a polynomial, could be an exponential, or any combination. Okay. So this is what we have dealt with so far in algebra. Now let's move to calculus. In a differential equation, the functional form of the function is not specified. Instead, the differential equation shows how the functions and its derivatives are related. Then the goal is not to find a specific value of the function, but instead to find the functional form. Here's an example of a differential equation from electrical engineering. Q is the charge on a capacitor, and it varies with time. So Q of t is the function we are seeking. We don't know what it looks like. It could be an exponential, it could be sinusoidal, it could be some rational function, it could be some polynomial. We don't know what it is, but we know that there is this relationship between Q, its first derivative, and its second derivative. So this is a differential equation for Q of t. It does not specify the functional form of Q of t. Instead, it specifies some relation between the function Q and its derivatives. The goal is to find the form of the function Q of t. Find out if it's an exponential. Find out if it's a polynomial. Find out if it's sinusoidal. That's the goal of a differential equation. Here's an example from physics. Many differential equations do arise from the application of forces in mechanical systems. Okay, and one is very famous. It's called simple harmonic motion. And I'm going to describe it now in terms of a mass oscillating on the end of a spring. So say you have a mass on the end of a spring, and x of t is the position of the mass. I don't know its functional form. It could be sinusoidal, exponential, who knows? I don't know what it is. I just know x is going to be the location of the mass on the end of the spring. It's going to vary with time. So say you pull or push on the mass and you displace it from its equilibrium position. The spring has restoring force and it will pull the mass back towards the equilibrium position. It overshoots and then it oscillates back and forth, right? The equation that describes the situation is the force that you pull is minus k times x. The minus sign is for the restoring force of the spring. Okay, you're going against the spring. And x is some function of t. It's a position. So x of t is the displacement of the spring as a function of time. We know what force is. Force is mass times acceleration, and acceleration is the second derivative of position. So let me write this a little more clearly. What we have here is x of t, which is the position or the location of the mass on the end of a spring. It's like we got a spring here, and we have this little mass on the end of it. Okay, and I'm going to put a coordinate system to it. Alright, let me just run this coordinate system here. Here's x. Okay, and now x is going to vary. If you push on the mass, you're going to start it back here, then it's going to move forward, it's going to move back, it's going to be forward, and then finally it'll settle down, back down to its equilibrium position. So here is the location. We'll call it x, and it varies with t. I know that the force on it will displace it, so F equals minus k times x of t. K is a constant for the spring. Remember, if you have a real stiff spring, like in an old car, K will have a very large value. If you have a little spring, say in a watch, K will have a smaller value. It won't take much to displace it. But what do I know about force? I know that force is mass times acceleration, and I know that acceleration is the second derivative of position. So I'm going to equate these two terms right here, and I get this differential equation. Mass times the second derivative of position equals minus k times the first. This is a differential equation. I don't know what x of t is. I don't know if it's sinusoidal, polynomial, exponential, or some other functional form. I don't know what it is. I just know that its second derivative equals the mass times the second derivative equals minus the spring constant times the position. The goal is to find the functional form of x of t. And at first, this might look impossible, but there are several classic solutions, and then there's several methods to find this form. So to summarize, for the spring, we have this differential equation. The second derivative equals minus k over m times the function itself. And now I have to find the form that satisfies this differential equation. And what I'm going to show you now is the solution, and then verify it by taking the derivatives and plugging it back into the equation. This is just to help you understand what a differential equation is. Okay, here I'm going to give you the solution. X of t equals some constant a times the cosine of the square root of k over mt plus b times the sine of the square root of k over m times t. To verify that this is a solution of the differential equation, I have to take two derivatives. So I'll put the second derivative here, and that better equal minus k over m times this form right over here. So I'm going to do that now. So here are the first two derivatives. If I take the first derivative, I get minus a times the square root of k over m times the sine, k over mt plus b square root of k over m times the cosine of the same argument. Okay. Now I take another derivative. When I take the next derivative, I get minus a k over m times the cosine plus minus b times k over m times the sine. I'm going to factor out these terms, k over m, and I'll factor out the negative sign. When I do that, I have minus k over m times this. If you remember, which you probably don't, and I don't blame you, from the other page, x of t was a times the cosine, root k over m times t, plus b times the sine, square root of k over m times t. So you see, after I took the second derivative and did a little bit of a manipulation on it, I ended up with minus k over m times the function itself. That shows that this functional form satisfies this differential equation. Whether it's the only one that satisfies it, that's a whole other subject, but this functional form does satisfy that differential equation, and that's what we mean by solving a differential equation. It means finding this x of t, finding the functional form. In this case, it was a cosine plus a sine, and verifying that it does satisfy the differential equation. Here's another example. The catenary is a shape, rather the height, of a cable suspended between two towers and is subject only to gravity. So here's what we get. So say we have two towers, a tower here and a tower here. Okay, and now we're going to take a wire and suspend it here and then just let it fall. All right. It falls under gravity. The shape that it assumes is called a catenary. Right. And if you work through the physics of this situation, you find out that this shape, which I'm going to call y of x, let me put a coordinate system to it. I'll do that in green. Oh, that's a wide coordinate system. Okay, so here's, say, my x-axis, and this is the y-axis. So y of x is the shape of this cable. All right. Here's the differential equation corresponding to this cable, and it's acted on only by gravity. It's a second derivative of y of x, y being the height of the cable above the ground, equals rho, the density of the cable, times the acceleration due to gravity, all right, divided by t, times the square root of 1 plus the second derivative, the first derivative squared. Okay. So here we have the same equation, same idea. We don't even have the function y of t in here. Instead, we have a relationship between the second derivative and the first derivative. Right. The goal is to find the functional form for y of t, and this is what it is. Okay, y of t, y of x equals t over rho g times a hyperbolic cosine of rho g x over t. Now you can verify this is a solution by taking the first two derivatives, plugging them back into this equation, and showing it is an equality. The second derivative has to equal rho g over t times the square root of 1 plus the first derivative squared. And that does indeed work. Okay, note, just as an aside, if you have a cable like on a bridge, and you have those little wires that hold on to it, that is not a catenary. Okay, you're pulling the wire into the shape, so this is not a catenary. Only gravity acts on the wire here. Okay. So in other words, a differential equation specifies some relation between the function and its derivatives, but it does not specify the function itself. The solution of the differential equation is the form of the function. Finding the function is obviously not a trivial exercise, but some have already been found, such as for the catenary and for harmonic motion. There are other classical solutions. These are helpful, and then there are other methods. This is the crux of the whole situation here. If you don't understand what's going on here, the whole rest of the chapter will make no sense to you. So this is not an algebraic equation where we're trying to evaluate the function. Instead, it's a differential equation involving the derivatives. We are trying to find the functional form the form of the function itself.